Every physical machine eventually hits a hard ceiling. You can only pack so many CPU cores onto a motherboard, and the local disk controller can only handle a finite amount of concurrent input and output before requests start queuing. Traditional replication doesn't bypass these limits. Copying the exact same dataset across multiple machines provides high availability if one server fails, but it doesn't increase the total storage capacity or the peak write throughput of the system. To push past the boundaries of a single machine, you have to introduce partitioning. This involves breaking a massive dataset into distinct, non-overlapping subsets, often called shards or vnodes, and assigning each piece to a different physical server. By doing this, you achieve horizontal scalability. You multiply the absolute storage capacity and the concurrent request throughput by the number of nodes in your cluster. Splitting state across a network changes the underlying mechanics of data access. You are forced to navigate a mathematical tension between three competing goals: write distribution, read locality, and cluster elasticity. There is no algorithm that maximizes all three. Engineers must design architectures that trade efficiency in one area to handle the specific read and write skew of their application. The first design decision is determining exactly how to map a massive logical key space to specific physical hardware using primary keys. We can visualize the data as a dictionary. Range partitioning slices this continuous dataset into adjacent blocks, often sorted chronologically. This layout makes analytical queries highly efficient. Spatial locality ensures you only interact with a single physical node to read that continuous block. The operational flaw emerges on the write path. If your data uses sequential identifiers like timestamps, all incoming traffic routes to the newest chronological block. A single machine is saturated, while the rest of the cluster sits idle. To eliminate these sequential hotspots and force the cluster to share the load evenly, systems turn to hash partitioning. Instead of sorting keys sequentially, the incoming primary key passes through a cryptographic hash function, like murmur3. This produces a randomized output, distributing records evenly across every available node. This guarantees uniform write distribution, but it discards spatial locality. Because sequentially related records are scattered, a simple chronological query must fan out and interrogate every single node simultaneously. This scatter-gather read path can saturate network I/O, making broad-range scans computationally unviable as the cluster grows. Systems like Cassandra use a compound key architecture as a compromise, reclaiming spatial locality within a hashed key space. The system hashes a primary partition key, like a user ID, to ensure all records belonging to that user are routed to the same physical node. Once the data reaches that specific machine, a secondary clustering key physically sorts the localized records on disk, preserving contiguous scans within that specific node. Even hashing has limits. If a single logical key, like a celebrity profile, receives millions of requests, the hash function still routes all that traffic to one machine, creating a hotspot. Primary key routing involves a zero-sum choice. You can optimize for contiguous read locality, or you can use hashing to ensure uniform write distribution. Primary keys handle direct lookups, but applications inevitably need to query data using other attributes, like searching for users by city or email. These secondary attributes have no mathematical relationship to the primary partition mapping, which forces an architectural divergence in how we build indexes. The first strategy is the local index. Each physical machine maintains its own isolated index, mapping the secondary attributes of the records stored locally on its desk. This optimizes the write path. When a record is updated, the database only modifies the primary data and the localized index on that same machine. The read path, however, requires a broadcast. Because the secondary attribute doesn't indicate which machine holds the data, a query must hit every node in the cluster and gather the results. This parallel execution introduces a significant operational risk. Because the query isn't finished until the last node responds, the entire request is at the mercy of the single slowest machine in the cluster. As this chart illustrates, 3 partitions might return results in 10 milliseconds, but if a fourth takes 150, the user waits 150. This is tail latency amplification, where one outlier dictates the performance of the whole system. The alternative is the global index. Here, the index itself is partitioned by the search term, acting as a directory that maps an attribute back to the scattered locations of the original records. This optimizes the read path. A query requires only a single index lookup to locate every relevant record, regardless of where they live, but the write path bears the cost. Modifying a single record now requires the primary node to execute cross-network updates to whichever nodes are hosting the relevant global index partitions. Because these cross-node transactions throttle throughput, systems often update global indexes asynchronously, prioritizing write speed over immediate consistency. Ultimately, secondary indexing dictates whether an architecture is optimized for fast, consistent writes or fast, eventually consistent reads. Distributed infrastructure is not static. Hardware inevitably degrades, and capacity must adapt for stability. When the cluster topology changes, the system must redistribute the data to keep the load even across the new set of machines. One common instinct is to route records using simple modulo arithmetic, dividing the hashed key by the total number of active nodes. Relying on the node count as a mathematical denominator is a fragile approach. If you add a fifth node, the denominator changes, and the modulo result for nearly every single key in the database is recalculated. Instead of only moving the necessary data to the new machine, this forces the cluster to shuffle nearly its entire key space across the network, saturating I/O and risking cluster failure. The solution is to decouple the concept of a logical partition from the physical hardware underneath it. Systems achieve this through fixed partitioning, using virtual nodes or vNodes. The database generates an over-provisioned number of logical partitions, say 1,000, regardless of whether there are 4 servers or 40. When capacity expands, the total number of logical partitions remains the same. The new machine simply claims a fractional percentage of those existing vNodes. The vast majority of the data stays put. This follows the core rule of operational elasticity. A rebalance should move only the absolute minimum amount of data required to reach cluster equilibrium. Decoupling the data map from the hardware count is the prerequisite for scaling a database horizontally without overwhelming the network. These 3 axes provide the structural framework for how data is distributed and accessed in a partitioned system. Primary keys dictate data placement, secondary indexes determine query paths, and virtual nodes dictate dynamic elasticity. The final requirement is service discovery, how a client application finds the specific IP address that holds the partition it needs. This is handled by a routing tier, which acts as an intermediary between the client and the cluster. This gateway must maintain an up-to-date map of the active cluster topology. Using consensus algorithms or gossip protocols, the routing tier detects hardware failures in real time, rewriting its map to steer client requests around offline nodes. There is no universally perfect distributed database. Architects must choose systems based on which trade-offs align with the dominant read and write patterns of their application. While partitioning solves the hardware limits of a single machine, splitting data across a network introduces the risk of fragmented operations. If a single logical transaction spans multiple different partitions, how do we guarantee data integrity if one of those network links crashes mid-write?